Thank you for introduction. Hi everyone. My name is, can you see the screen?
Yeah.
Yeah. Okay. Okay. Hi everyone. My name is Takuya Miyashita. I am affiliated with Kyoto University in Japan, and I'm currently visiting researcher at NOAA PME on the seacoast at the University of Washington. Today, I will introduce the GeoClaw developments I have been working on. And as title suggests, this mainly focuses on extensions for Meteotsunami simulations. So let me first give an overview of today's talk. The animation of the right shows the simulation of the Meteotsunami generated by the 2022 Tonga volcanic eruption. So unlike the earthquakes generated tsunamis where the seafloor displacement is given, meteor-tsunami simulation use atmospheric pressure at the sea surface. And then horizontal pressure gradient acts as a driving force of the waves. In this sense, the formulation is similar to storm surge modeling. So we extend the existing storm surge modules in GeoClaw to simulate meteor-tsunamis. So first, using the Tonga event as an example, I will explain a case where the atmospheric pressure fields are provided as netcdf files. And this approach allows us to directly use atmospheric fields computed by meteorological or climate models in GeoClaw. Next, I will introduce an alternative approach where the atmospheric pressure field is defined directly within the source code instead of using external files. If we assume a pressure disturbance described by a simple set of parameters, we can incorporate it into the model by modifying the Fortran source code. But because of this approach has been implemented recently, so I will show a few test cases and then discuss possible direction for future improvements. Before going into the details of the implementation, let me explain the motivation behind this work. The 2022 Tonga Meteotsunami was a very intriguing event at Amami in the Ryukyu Islands in the southwestern Japan. A maximum tsunami amplitude of about 1 meter was observed, uh, like here. However, reproducing this large amplitude was very difficult. Even when we increased the coastal resolution to properly capture the Bay resonance, the result did not improve significantly. And this suggests that there may be some amplification mechanism offshore. What is particularly interesting is that the amplitude recorded at two nearby dart stations were only about 3 centimeters. The upper two plots show the detailed tsunami amplitude observed at these data stations. The black line in the lower plot shows the waveform observed at Amami. So in other words, the wave was amplified from about 3 centimeter offshore to about 1 meter at the coast over a distance of a few hundred kilometers. To investigate this amplification mechanism, we decided to simulate meteotsunamis using GeoClaw. So based on this motivation, the objectives of today's talk are as follows. First, I will introduce our modification to GeoClaw for Meteotsunami simulations and briefly present some of results we have obtained. And then next, I will introduce an approach for incorporating parameterized atmospheric pressure fields directly within the source code. And then finally, I will talk about the research we plan to pursue after this development. Now, let me explain how we simulate meteor tsunamis by reading atmospheric pressure data from NetCDF files. In the latest version of GeoClaw, I understand that some functionality for storm surge simulations using NetCDF input already has already been implemented. But we started developing, sorry, but we started developing our own approach several years ago. So please note that what what I will show here is our implementation. Uh, as I mentioned earlier, this approach is based on modifying the storm surge modules. So relevant source files are located in the search directly under the geolib directory. In particular, we modify data storm module.f90 and storm module f90. In the makefile of the simulation directory, we first exclude the original versions of these files from compilation. Then we copy and modify these files locally and include them by specifying their paths uh, in the modules variable. In the data store module .f90, we implement how to read NetCDF data. Because this requires a NetCDF Fortran, we use the nfconfig command in the makefile to properly link the required libraries. Then let me briefly introduce the main findings obtained using this model. And as a result, we were able to reproduce the approximately 100 centimeter amplitude observed at Amami Station using only a relatively weak atmospheric pressure disturbance of about 2 hectopascal. This indicates that the accurate representation of fine-scale bathymetric features such as offshore ridges is crucial for this amplification. We also found that if the offshore resolution is not sufficiently high, this amplification cannot be reproduced. This is a key difference from typical earthquake tsunami simulations. For seismic tsunamis, relatively close resolution in deep water on the order of several thousand meters does not significantly affect the overall accuracy. Then here, I would like to discuss the main challenges of this approach. And first, when using external atmospheric data, high resolution input files are required, which leads to very large data sizes. In the Tonga case, we use the data with 1 minute temporal resolution and about 6 arc minute spatial resolution. As a result, for only about 14 to 16 or 70 hours of simulation, the atmospheric data alone amounted of several tens of gigabytes. And another issue is temporal resolution. If the input time interval is not sufficiently small, temporal interpolation tends to smooth the pressure field. In particular, when the pressure disturbance moves rapidly, the peak pressure may not be captured between two input time steps. This can lead to an underestimation of tsunami amplitude. And these are also challenges in coupling with meteorological models. For example, atmospheric models often use different map projections, so preprocessing is still required before the data can be used in GeoClaw. In addition, atmospheric models are typically fully, fully three-dimensional, including a vertical structure, and therefore much more computationally expensive than tsunami simulations. Because of this, real-time prediction using coupled model is still difficult at present. So now let's move on to the next approach. As I mentioned earlier, using external input files can lead to very large data sizes. If the pressure field can be described using a simple parameterized function, it is often more efficient to implement it directly within the source code. So in this work, we take this approach to introduce a parameterized pressure wave. The main file we modify is model storm module.f90. Unlike the data storm module.f90, which handles external input, and models storm module.f90 contains the implementation of analytical models for atmospheric pressure and wind fields, typically used for hurricanes and tropical cyclones. The, each storm model is identified by a different number of variable storm specification type. And because the values from 1 to 9 are already assigned to existing storm models, we introduced a new type, storm specification type equal 10. In this new option, we implement the moving atmospheric pressure disturbance. And as a first step, we assume a simple sinusoidal pressure wave that propagates at a constant speed. We then apply this model to an idealized test case. Here, we consider a bathymetry consisting of a uniform slope between two regions of constant depths. A pressure disturbance propagates from the shallow region toward the deeper region, generating waves along the way. The left panel shows the sea surface elevation, and the right panel shows the prescribed moving pressure disturbance. And as you can see, the wave is trapped and amplified along the slope. Then, although the pressure amplitude is only about 4 hectopascal, the resulting wave height exceeds 30 centimeters. And as you can see, this trapping and amplification depend not only on the amplitude of the pressure disturbance, but also on its propagation speed and direction. Therefore, it is important to investigate the conditions under which this amplification occurs, both theoretically and numerically. Then here's another example. This is a simulation using realistic bathymetry of the west coast of Kyushu in southwestern Japan. Along the Kyushu coast, Meteotsunamis of about 30 to 50 centimeter occur several times a year, and occasionally it exceeds 1 meter. And to the west, the East China Sea forms a continental shelf, shallower than about 200 meters. While closer to Kyushu, there is a deeper region of around 2,000 meters known as the Ryukyu Trough. So note that the Ryukyu Trench is around here and the Ryukyu Trough is around here. So the overall structure is quite similar to the idealized case I showed in the last slide. From the figure, we can see that the waves are again trapped and amplified along the specific depth contour. In particular, the amplification occurs when the moving pressure disturbance constructively interacts with the trapped wave propagating along the slope. This leads to the formation of a forced wave that enhances the overall amplitude. To better understand these processes, we aim to quantitatively evaluate the conditions under which amplification occurs and ultimately apply this knowledge to area prediction and hazard assessment. So I'm running late, but I have to wrap up. But now let me briefly discuss the theoretical background. This example I have shown so far can be approximated by the bathymeter like the one shown in this figure. Here, I focus on free waves independent of moving pressure disturbance. We divide the domain into three regions, two regions of uniform depths and a sloping region in between. For each region, we consider the general solution. We assume a unit amplitude incident wave and represent the other wave components using complex coefficients A, B, C, and D. Then, using boundary conditions, we can then determine the coefficients. By applying the boundary conditions, we can determine the coefficients as shown on this slide. Then, the visualization of these solutions is shown on the right-hand side. From this, we can see that trapping characteristics depend on the direction of wave propagation. And, however, this results corresponds to free waves and periodic waves. However, the dominant direction of wave trapping not expected to differ significantly from forced wave case. In this way, by combining insights from numerical experiments and theoretical analysis, we aim to better understand the trapping and amplification mechanism of meteotsunamis over this type of bathymetry. And that's all. I'm running late, so that's it. Thank you for your attention.